Hello everyone. Today we are going to start the first day of our Physics 11 class. Now, physics is a science course. That means eventually we will have to take data and do measurement at some point, right? But there are actually two types of measurement that people can make. Now, this is almost specifically only concerning about physics and not as much in other science. Now, the value that we are concerned with is direction. Okay, direction. Now, some measurement leads direction in order for it to make sense, but some measurement doesn't. For example, if you want to measure something's mass, which is in, kilogram, right? So mass is measured in kilogram. So let's say you want to measure something's mass, which is measured in kilogram. You don't have to call the direction for that measurement. For example, let's say you are a 60 kilogram person. You don't have to tell someone, hey, let's say someone asks you, what's your mass? And then you say, well, 60 kilogram facing southeast. You don't have to add the facing southeast to the description, right? Are you going to weight any different if you face southwest instead of southeast? No, right? You don't suddenly change weight because of your difference in your orientation. So therefore, mass is a type of measurement that we call scalar measurements. Scalar measurements are measurements that you only need a number associated with the unit, but you don't need a direction. You don't need to tell someone which way you're facing or which way you're going. Okay, so for example, the mass of an elephant is exactly the same. Doesn't matter if you make the elephant stand up to measure its mass, or sit down, or lie down, or turn it upside down. The mass of something is always the same regardless of the direction of the object, right? Does that make sense? Now, mass in our equation, so if you look at your formula sheet, every time you see a m in the equation, that's where you will put in the mass. Now, there are other quantity that concerns us. So, for example, if you want to measure how fast something is moving, we say we measure the speed of an object, right? Now, in physics, we prefer using meter per second. So, how many meter does the object travel in 1 second? That is not the same unit that you actually see in your car's dashboard, for example. That is measured in kilometer per hour, km per hour. And we will usually have to change that into meter per second when we have to use it. So now speed is a scalar measurement. So for example, if someone asks you, how fast are you going right now? I'm going at 30 kilometers per hour at a school zone. That is the speed. You don't have to tell people that you're going at 30 kilometers per hour facing south or facing east. If the police ask you, how fast are you driving? Where are you driving? You say 60 kilometers per hour. You don't have to say, I'm going down number 5 street and doing something, right? You don't have to say which direction you're going. The speed of a vehicle or person or an animal in that regard is magnitude only. So when someone asks you for your speed, they expect you to tell them the magnitude only. And that is also a scalar measurement. Now, we will go into the unit conversion in a little bit. For example, like kilometer per hour to meter per second. You should know how to do that. It's easy enough in those type of situations, but we will go over it a little bit. Now, most of the time, okay, so let me sidetrack a little bit about unit. So now, most of the time, we are concerning about meter per second to km per hour. Because in a lot of situation, for example, dealing with vehicles, cars, and trains and airplanes, there a lot of time they're measured. Units are measured in the speed is measured in km per hour or miles per hour if you're living in the U.S. But meter per second is the international standard for science communication. So that means in everyday life, yeah, you can use km per hour. But when you're actually writing science, writing physics, for example, you must use meter per second. You cannot use km per hour. You cannot use miles per hour. You can only use meter per second. There is a set standard from the international committee called the SI standard, which give us rules about which unit we can use in what situation. So for example, mass in physics in the international standard is always measured in kilograms. So I'm listing all the international standard in here too. So mass is always measured in kilogram, speed is always measured in meter per second. So what happens if you have a question where the object has a mass but it's in gram? Well, you have to convert it to kilogram before you can proceed and use any of the equation on the formula sheet. You look at those, maybe 20, 30 equations on the formula sheet that you got on the first day, right? Every single one of those equations require you to use all the information in the international standard. That means if you suddenly substitute something that is not meter per second into a location where you see a v, which representing speed, the equation will simply fail and you'll get the wrong answer 100% of the time. Okay, so now let's make sure we remember that. So now meter, so for example, meter, right? So meter, we have 1,000 meter. Okay, so let's say kilometers, right? So 1 kilometer is equal to 1,000 meter because kilo means 1,000 times 10 to the 3, right? Now, and then for minutes and second, or hours and second, so 1 hour, on the other hand, so 1 hour has 3,600 seconds. Now, because 1 hour has 60 minutes, right? So if you multiply by 60, you get minutes. And then 1 minute has 60 seconds. So you multiply that by 60 again, you get 2 seconds. So 1 hour is 3,600 seconds at the end. Okay, so if you have a speed that is measuring km per hour, which is very common when you're driving, then you have to plug that speed into a equation that you find on the formula sheet, which you cannot do with km per hour. So for example, let's say you have a school zone speed, right? The school zone speed is, in some location is 30 kilometers per hour. In some locations, 40 kilometers per hour. So let's say it's 30 kilometers per hour. That's the school zone speed limit, right? So what is 30 kilometers per hour, for example, into meter per second? Right? So if I want that into meter per second. Now, the long way, or I guess the proper way to do this is actually such to the following. So you do km per hour. So you write it like this, km per hour. And then you use the conversion factor that are over here. So what you do is you think about the unit that you want to keep and the unit that you want to cancel, and then you adjust the proportion accordingly. So for example, I'm going to use the first rule first, which is km going to meter, because at the end I want meters, right? So what I would do is I'll multiply by a fraction which has km and meters in it. Now, where should I put km and where should I put meter? I should put km in the bottom and I should put meters on the top. Now, how come? Because I would like to cancel out that kilometer and I will only have the meters left at the end. Then I deal with the unit first and then I put the numbers in. The number is what? Well, how many kilometer is a meter? Oh, so that's where that information comes in. Exactly. So for example, in this case, I know that 1 kilometer is 1,000 meters. So I just put 1,000 on top and and 1 on the bottom, right? And then I multiply by another conversion, because right now, if I just do this, the unit for this quantity is going to be meter per hour in the bottom, right? Because the only unit you have left on the top is meter. The only units you have left in the bottom is hour. So right now at this moment it's actually a meter per hour business, which is not exactly what we want. Okay, so we want the meter to be there, but we also want the second to be there. So we are going to get the second in there. So getting the second in there, again, same thing, set up a fraction. So you can do this with like chemistry and all the other unit conversion that you ever need to do. This method works. It's a slightly longer method, but it works. Okay, so what do I want to get rid of? I want to get rid of hours, right? At this moment, hour is in the bottom. So in this fraction, I'll put hours on top and I'll put my desired unit, which is second on the bottom. Now, then you fill in the number, which is how many hours is in 1 second, or how many seconds is in 1 hour. 1 hour is 3,600 seconds, right? And during this, what happened is the hour on the top cancel with the hour on the bottom right here. So at the end, you look at what you have left. Now, in terms of numbers, you have a 30 multiplied by 1,000 dividing by 3,600, right? Right, that's what you have left. I have these three things left: 30, 1,000, 3,600. So you do that in your calculator. But in terms of units, what do you have left? In terms of units, I only have two things left: this meter thing and this second thing. So therefore, this is automatically, once you're done with the actual conversion, meter per second, ladies and gentlemen. So it's 330 times 1,000 divided by 3,600, and that's how you turn it into meter per second. Now, I know doing this is the proper way, but in physics, sometimes we have to do this kind of conversion in like a second. We can't spend time writing all this out. So there are some mental shortcuts that you should take. For example, now in this case, think about the numbers. You're multiplying by 1,000 and immediately dividing by 3,600, right? So what does that actually combines into? Like when you're multiplying a number by 1,000 and then immediately dividing by 3,600, you are basically dividing by 3.6, right? Like that's essentially what you're doing. Like this whole thing is dividing by 3.6. It's times 1,000 dividing by 3,600. So therefore, here's a shortcut. Okay? From meter per second to, from km per hour to meter per second, all you have to do is divide by 3.6 if you want to go that way. Okay, so you know what? I should write it so that I can go both way. Like, so meter per second. So if I want to go this way versus if I wanted to go back, sometimes they might want you to express your answer in terms of km per hour, and then you have meter per second to begin with, and you can go back. So divide by 3.6 if you want to go from km per hour to meter per second, multiply by 3.6 if you want to go back. Okay, so this is kind of like a shortcut. Now, it only works with km per hour and meter per second though. So if you only have km, just multiply by 1,000, it will go to meter. If you only have like a time that you need to deal with, so for example, like when they say, oh, the time is 30 minutes, and then you need to substitute that into one part of the equation, but you cannot use minute, right? You have to use second because that's the internationally accepted unit. Then you don't have to go through remember the shortcut. You just have to remember, wait, come on. Minute times 60 is seconds, right? 1 minute has 60 seconds. So just do 30 times 60 and then you'll get that in seconds. Okay, so this shortcut right here, the one that I'm highlighting right now, right, is only good if you're converting this combo unit, km per hour to meter per second. It's only for one use and one situation only. But that is, this situation is common enough in physics that everyone needs it. Okay, you use it all the time. Okay, so now moving on. Okay, so now let's continue with all these units. So we will actually speed up a little bit. So for example, time, as I said earlier, is measured in second. And in the equation, when you see the symbol T, that always represents time. Now, sometimes you will see a capital symbol, which is big T, and this is temperature. Now, again, I'm writing this in the column of scalar quantity. That means these are quantity that does not need direction. Time doesn't need direction, right? For example, you're baking a turkey and you're asking, hey, how long should I bake it for? And your parents told you that, hey, you should leave the turkey in the oven for 4 hours. Facing northwest? The turkey should face some, maybe you have an uneven oven that one side is hotter, the other side is colder. But usually you don't have to specify that, right? Your turkey's direction has nothing to do with the time that it takes to cook the turkey. So therefore, time doesn't need direction. Someone asks you, what time is it right now? It's 5 o'clock when I'm facing south. See, that doesn't make sense. You don't have to say you're facing south. Why do you need to tell people you're facing south? It's not like it's not 5 o'clock if you're facing east, right? So time doesn't need direction, magnitude only. Temperature doesn't need direction. 400 degrees Celsius is 400 degrees Celsius in the oven, right? Okay, 400 degrees Celsius is a lot. Please don't set your oven to 400 degrees Celsius. I meant to say 400 degrees Fahrenheit. Now, but in science, right, we cannot allow for more than one unit for one thing. Therefore, temperature, we have decided internationally, in the scientific community, have decided we are all going to be using degree Celsius, unless you're in the American and you want to be different, right? Degree Celsius is the number. So we will have a section, a chapter later on that talks about the thermal energy of an object, like the energy of the heat of an object, and we will use temperature in that chapter. Every single temperature has to be in degree Celsius. Now, we have other scalar quantity which will come in later chapter. For example, the quantity for energy is measured in joules. I think you have learned it in previous science class, joules. So that is also a energy is like money. If you have energy, you can do stuff. If you have money, you can buy stuff, right? So it doesn't have direction. Money doesn't have direction, right? How much does this apple cost? $2. If you're facing 30 degrees from the south, you don't say that. Right? You don't say that. It doesn't make any sense. Okay. Now the last one, which is actually very important too, is distance. The distance or the length of something. So now the length of something, right? So for example, the length of a book is going to be, so for example, let's say the length of a book is 30 cm, 30 centimeters. If you put the book sideways, the length of the book is still 30 centimeters. If you take the book and stand it up, the length of the book is still 30 centimeters. Changing the direction of the object doesn't change the length of something. And sometimes we only care about, so for example, if you wear your Fitbit or your Apple Watch and you go out for a run, right? And when you come back, you probably have some type of location tracking that you turn on. So it tells you how far have you run. That is a distance. That's the length of your running exercise. Now, you have probably made a lot of turn and twists, like you go to the park. It's very unlikely that you're running like in one straight line and never turning back, right? Never turning, never. So the what Apple Watch actually measure, or what your Fitbit actually measure, is the distance that you have traveled, which does not have direction. It's only like it's assuming that you're walking in a straight path, even though you're not, right? Sometimes those kind of measurement is useful. So for example, when you're doing exercise, you don't really care about which direction you're going, as long as you're going somewhere, right? So the fitness tracking information giving you distance makes perfect sense, right? But I'm sure you have turned somewhere. Like, don't tell me that you go exercise and you never like turn. That doesn't make sense. You'll never come home if you don't. Well, actually, if you go all the way around the earth, you can come home, right? If you never turn and you just walk in a straight line, and the earth is not flat, by the way, it's rounded, it's a sphere, you'll eventually come back to where you are, maybe after like 3 years, right? Okay. Now, the other main family of measurements are measurements that lead a direction, otherwise it is incomplete. So not only that you lead a number, you also lead a direction. Now, as far as direction goes, so for example, let's say someone asks you to open a door. They say, well, to open this door, you need to apply a force. Now, force, which is measured in Newton, should be in grade A science, right? So force measuring in Newton, which has a symbol F, force measuring in Newton leads a direction usually. Because, for example, if you only tell people how much force to apply, but not tell them which way to push. Have you ever, go to a shopping mall, or maybe, just going to some places that you're not familiar with, and you're trying to open a door or open a cabinet, and you try to pull it and then it doesn't move, and you try to push it, it doesn't move, and then after 5 minutes you realize it's a sliding door. You should have slide it to the right or slide it to the left, so it's not like a pushing or pulling door. See, without the direction of the force is actually not as useful. So you can say, yeah, you just need 30 Newton to move that table or move that chair. But telling people which direction is the force applied at is a good thing. So think about, like, you pushing a box, right? You pushing a box with a force, right? So let's say the force is 30 Newton. But then, wouldn't that be useful to tell people, hey, you should push that box to the right-hand side, please? Because 30 Newton pushing to the left-hand side is a totally different scenario, right? The box will sliding to the left, and that's not something that you want. You actually want the box to go to the right. Okay, so force, for example, right, leads direction. So direction, we usually put it right behind the numbers, the magnitude and the units, and we use a square bracket to represent the direction, right? Now, as far as directions go, it can be up, down, left, right. So it could be those things. In some situation, right? So it could be like up, down, left and right hand side. Now, in other situation, it could also be north, east, south, west, like that kind of direction. And it can actually get even harder. It can be, some type of direction, which we'll see, I think in maybe 5 days class or something like that. It's like north 30 degree, south or I don't know if you have seen this kind of direction before, or there's still one more type of direction that sometimes people give. So people can say 30 degree north, north 30 degrees south makes no sense. North 30 degrees east. Okay, that means you're facing north and you turn 30 degrees to the east. Okay, now the last type is this type, which is 30 degree north of east. Okay, so now we will talk about these different type of direction measurement later on, but just understand that there are different ways you can tell direction. Some simple direction is just up, down, left, right, north, east, south, west, but there are other compounded directions where you have to tell them there's a degree involved where they should turn. Okay, but some quantity leads directions. That's the main focus. Now, what else leads direction? So over there on the other side, we have speed. And now we have velocity. Velocity is also measured in meter per second. So it's exactly the same as speed over there, right? It's exactly the same as speed, except this is the direction version of the speed. It uses the same symbol, except you add a little arrowhead, like arrowheads on it. Sometimes if you need to make a note on the fact that, hey, this is the vector quantity, that means you need direction, then you add a little head on the symbol. So let me write bigger. So you add a little head on the top, people will understand that, hey, this is like a half arrow, right, on the top. People will understand that, hey, this quantity leads direction. Please give me direction. Please don't just leave your answer with a number only. Now, when will be a situation where you actually lead direction? When you're talking about your speed, which is called velocity, by the way. So let's say you're driving, right? And your GPS is showing how fast you're driving. But if you look at the Google map, you also have a direction, right? So if you have a satellite view of your car not only has a speed, which is moving at, it also has a heading. The heading is the direction of the car. So for example, someone will say, hey, I'm driving 30 meter per second to the south, right? So this is a velocity. If you're saying I'm driving 30 kilometers per hour and don't say direction, that's called speed. Okay, so speed, no direction. Velocity, you say it with a direction so that people know more about the information that you're giving. Okay, so what else? Now, there is another one. So we have distance over here, and there's a direction version of this. It's called displacement. Okay, so this is the same thing as distance, except that you need directions for it. So displacement, so D with a little head. Okay, so displacement and distance is the same thing, except one does not have direction, the other one does. So distance is like, again, right? I give you two examples. It's like, when you're running and your Fitbit say, okay, so here are the distance that you have covered, or you have a measurement of the length of an object, so it doesn't matter how you put it, it's exactly this. You don't need direction for that. Displacement is your change in location. So for example, someone get off the bus stop, they try to visit you, and they say, okay, so you tell me that it's 2 blocks from the bus stop. But 2 blocks from the bus stop which way? Right? Is it 2 blocks from the bus stop to the right or 2 blocks from the bus stop to the left? See, without that direction, the 2 blocks from the bus stop information actually fails to tell the person where to go. So you can say, hey, to walk to the treasure, you need to walk 45 meters. And then people ask you where? No, I say 45 meters to the left, right? To the left. That would be a displacement. So if you say the distance with a direction, it's called displacement. It has direction now. It has more. It is conveying more information. Now there's one last one, which is called acceleration. And acceleration is every time you see an A in the equation in the formula sheets, right? That's acceleration. This is how fast your speed is changing, how fast you're speeding up or slowing down. Acceleration. Okay, so acceleration. This is measured in meter per second square. Okay, meter per second square. So that's actually a little square on the square on the second. Okay, so this we'll deal with in a little bit. Acceleration is just how fast your speed is changing. When your acceleration is positive, you are increasing speed usually. So, but there is a direction involved too. Okay, so now once we get all the units figured out, then we're starting kinematics, right? We're starting kinematics officially. Okay, so kinematic is the study of an object's motion. I think I've mentioned it on our introductory class yesterday. So kinematic is the study of an object's motion. Now, so there are some repeated information in here, but that's okay. So distance is the separation between 2 points, the length of an object, usually measured in meter, no direction needed. Okay, so for example, if you have a book and you measure this side as 30 cm, then that 30 cm is a distance measurement. You don't have to tell people direction. Okay, it's just the dimension of a book. Displacement. So for distance, we use the symbol d, right? So distance is d, whereas displacement is d with a little half arrowhead on top like that. So, okay, so that indicates that this is the vector. You need direction, please. Or you can say change in position. Change in position works too. So this is a change in. Now, in science or physics, you see these Greek symbols a lot. This is actually not English. It's not just me randomly drawing a triangle. This is a character, just not an English letter, right? This is from Greek. Is the Greek version of the D in our language, in our English. So that's called delta. Delta. Okay, you're learning actually a new language too. So delta. So delta means change in something. Okay, so delta means change in something. So if a quantity change, then we put this little triangle in front of the quantity. So when your location change, we call it displacement. So delta D means you're changing your location or changing your position, right? So your position change, you need a displacement because you need to know, hey, for example, let's say I have hidden your cell phone somewhere in your classroom, right? In the classroom. You ask me, Mr. Chang, where's my cell phone? I said, well, it's about 10 meters from you. I moved it 10 meters. See, that's a change in position. But without telling you direction, that you don't know where to look for it, right? Maybe it's 10 meters up, so it's in the ceiling. Maybe it's 10 meters down, so I bury it under the ground. Maybe it's 10 meters to the left, to the right, to the south, to the north, right? Maybe it's something 30 degrees south of east. So you need direction. Otherwise, your change in position makes no sense. Okay? Now, so change in direction, or for example, position, or your displacement is equal to final position minus initial position. So in physics, change in anything is always final quantity minus initial quantity. So delta D is the change in D. Now, because we're talking about direction, we also need to worry about plus and minus sign in some of the value to indicate direction. Now, it's generally accepted that if you're talking about the 4 basic direction, right? So the 4 basic direction, as in up, down. So up, down, right this way, and then left this way. So if you're talking about this like 4 basic direction, up, down, left, right, then we usually associate up and right hand side as positive. So the left hand side and the downward is negative. That's just convention. That means, traditionally people have been doing that. Now, same go with the mapping direction, north, east, south, west, exactly the same thing. So if you want to look at north, east, south, west, like that. Now, you need to memorize how to draw these type of diagrams. So like, for example, like this thing, you need to draw it for multiple times. very, very soon, many times. So you need to know how to draw that. North is on top, and then you just go go clockwise, and you say north, east, southwest, right? Okay. So for north, east, southwest, same thing. North and east are usually considered to be positive. So west and south, negative. Okay. So if an object moved north, then we will say they move in a positive direction, positive north. If they move south, then we put negative sign in front of it. So a lot of time this is the situation. So traditionally, just going back, we assign north and east as positive and south and west as negative. Okay, so now one simple example. So for example, you go from point A to point B, and this is how you travel, like right there. So you went from point A to point B. Okay, so your displacement or change in location is 10 meter, and you're going to the east. So we'll say 10 meter east, like that. Now, on the other hand, if you are going from, let's say, B to A this time, so you're going from like this way to that way, and this measurement is 50 meters, then you will say your displacement is, now, okay, at this point, you actually have two options. You can say 50 meter, and you can put west, right? 50 meter west. That is actually true. Or alternatively, you can also say negative 50 meters east. So negative, right? Negative of east. So negative of east is west. Okay, so you don't keep the negative and the direction sign. Think about it, that would be double negative, right? So for example, you don't say negative 50 meters because I'm going that way, and then you put west on it. If you do this, this means east is the negative of west, which is east. That doesn't make any sense. Okay, so you either write the direction down as a like physical, just write it down as a number, as a symbol, or you use the plus or minus sign to indicate that you're going the other way. Okay, so now two example, very quick. Now, someone walked 5 meter east and then 3 meter west. So that walking path is going to look something like this. So you're starting at A location and then going to B, and then so you're going from 5. So this is 5 meter going to the east, and then you kind of sort of turn around and then you go like 3 meter backwards. So you went 3 meter this way. So you end up being like over here at C, point C to later on, and this is 3 meters, right? So now, but because going west is usually negative, so that means the 3 should be a negative 3 and the 5 should be a positive 5 in this case, right? So what is the distance traveled? Okay, so think about it. If you're wearing a Fitbit, how far will the Fitbit set that you have moved? Right? The Fitbit doesn't know your direction. The Fitbit only know that you have moved your body. So in terms of distance, it will say 5 plus 3 meters, which is 8 meters. You have walked a total of 8 meters. Now, that is useful piece of information. I mean, yeah, you have walked 3 meters. That's true. You have walked a total of 3 meters, even though you turn. But what is your displacement, which is a vector? So now you need direction. So your displacement is going to include the direction. So you're supposed to add the two change in location together, but the first one is a positive 5. The second one is a negative 3. So therefore, overall, it's a positive 2 meters. Now, in this question, positive sign is associated with the east, so, because, in our picture, we just happen to draw positive with the east. You can decide that. You can tell people which way is positive, which way is negative. So therefore, your answer can either be this, or you can say 2 meter and just put east. Okay, so you put 2 meter east on it. That will be perfect. Okay, let's try another one. A cat walks 5 meters to the left to get a slack, which is a goldfish, not an actual goldfish. It's just a slack goldfish. See, We're not being violent in here. It's just those, goldfish crackers, right? And then 5 meters right to go back to bed. So you have like a kitty. I don't know how to draw a cat. There you go, cat. And then it is, so it goes 5 meters that way and 5 meters coming back to get goldfish. There you go. Now they're both 5 meters, right? Okay, so what is the total distance travel? Okay, so remember, distance doesn't care about direction. So as far as distance is concerned, the cat has walked 10 meters. It's 5 meters to the left, 5 meters to the right, but I don't care about direction. So any plus or minus sign is ignored, right? Even though walking backwards should be negative, so it's 10 meters in total. Now, however, if you are worrying about displacement, then the displacement of the cat, which is a vector, the displacement, which is the change in location. So first, oh, you know what? I actually drew this in the opposite way. No, I didn't draw it in the opposite way. I put the negative sign in the opposite one. This is negative. So you go 5 meters left first, and then you go back to 5 meters right. There you go. So 5 meters left, so negative 5 meters, and then 5 meters right, so 5 meters. So it turns out is 0 meters. That's your displacement, which is kind of weird, right? Well, but think about it. What is displacement? Displacement is your change in location. Let's say you're looking at a cat right now. The cat is on its bed. And then you turn around and then you start making yourself some lunch. And in the meantime, the cat did the thing that it did, which is going to get a goldfish snack and then come back. And then you finish making your lunch, prepping your sandwich, and you turn back. Where's the cat? The cat is still on its bed, right? So to you, not knowing what happened in between, what is the change in position of the cat? So I asked you, did the cat move? You will have to conclude that no, the cat didn't move, right? So the displacement of the cat is 0. So you see, displacement doesn't care about what actually happened in between. As long as you're starting and ending at the same point, your displacement, which is your change in location, is 0. Okay? So like, think about, like a funny thing would be, so let's say I'm looking at you right now. You are, so let's say, in a classroom, and then I turn around, you fly to the moon, you come back, and then I turn back, and then for me, your displacement is still 0 because I didn't know that you could fly to the moon and come back. Right? My only concern is where's your starting location and where's your ending location, and if they're exactly the same, then your displacement is 0. Right? Your total distance travel, it might not. So this is one of the first, confusing informations about this. All right. So let's continue with the next half sessions. All right, now let's continue to the next page where we are now going to look at speed versus velocity, which is just how fast is the object moving with or without direction version, right? So your speed is the one that doesn't have direction. It's your change in distance, okay, which also doesn't need direction per time. Your change in distance per like every second. So the equation, which is the first equation that you should find in your formula sheet, is velocity is equal to distance over time. Now look at this d. This d doesn't have the little hat on top, right? So this is just distance. Okay, the unit for that. Distance is measured in meter. A time is measured in seconds. So appropriately, if you're dividing them by each other, then the speed unit should be meter per second, right? Meter per second. Now remember, this is distance, not displacement. Okay. Now, for example, when you go out and you see a speed limit, see, that's called speed limit, not a. When you go outside and you're driving on a highway, you see a sign that says 80. Does that tell you the direction? No, that's why we call it a speed sign, not a velocity sign, right? This is your speed limit, not your velocity limit, because no matter which direction, that's why they don't have to tell you one, that you're driving at, you cannot exceed this limit. It's a speed limit. Usually the speed limit on the street is actually measured in km per hour, just a little side information. That is not kilometer per second, right? That's usually measured in km per hour. Speed is a scalar, just like displacement. Okay, you don't need direction, just magnitude. Now, on the other hand, velocity, which is the speed with the v symbol with a little arrowheads on top, is the change in your displacement per unit time. So therefore, the equation for that then is your displacement over time. So it's not distance over time. This is actually displacement over time. Of course, everything else is exactly the same. Now, this is the equation that you can use to find average velocity. And the unit, of course, is still measured in meter per second. If you so there are a few ways to manipulate this equation. I mean, you can solve this equation for d, then it will be displacement is equal to velocity times time. You can solve this equation for t, then it will be t is equal to distance divided by velocity. But you should know how to, derive this just from the equation, the first equation on its own. So, I mean, all the equation that I provided for you only has one version, the version that's most recognizable. In order to solve for the other thing, you will need to come back and think about the reason why we did those algebra review on day one. Is because you yourself need to be able to solve the equation for other things. Now, velocity is a vector, and then now we can get into some example. Okay, so once we understand the difference between vector and scalar, is basically pretty straightforward. A student travel 11 meters north. Okay, so there is a direction involved, and then turn around and travel 25 meters south. So that means this 25 meter should be a negative 25 meters because it's to the south, and south is generally assigned to be negative. Now, some of you might ask, why are we discriminating the direction south? Why is south always negative? No, south is not always negative. It's just that it used to be that traditionally we call north positive. So can you call south positive? Yes, you can. You just have to tell the people who is reading your work that you are calling south positive for this question. So therefore, at the beginning of the question, let's say in a question that you're doing, right? Let's say every single thing that they give you is south. So it will be stupid to put a negative in every single value. Why not just call the south direction positive? You can. You totally can call the south direction positive, but you cannot just think about it. You have to write it down. So if you write it down in the question, and let's say at the beginning, you say, let south be positive for this question. If you write down that sentence, then you can have south as positive for the entire question. Okay, so you could change it. It's just that if you're not going with tradition, you have to tell people that you're deviating from what they usually are comfortable with. So students' average speed. Okay, so I want average speed. Now, speed is distance over time. Okay, so total distance travel over, so total distance over time. So that's speed, right? Total distance over the time. Okay, so what is the total distance? Your Fitbit. Think about your Fitbit. Think about your Apple Watch. Think about your Samsung smartwatch. Your Google smartwatch. What would it say that you have walked? What would it say? 11 meters to the north, 25 meters to the south. So that's 36 meters in total, right? So in terms of your this distance is 36 meters without the direction. Okay. Now, time is 12 seconds. So time is 12 seconds. So we have that. So therefore, the total, so if you do that in your calculator, is 3 meters per second. Now, because this is supposed to be speed, I don't need direction. Okay, so what about the average velocity? Now, average velocity is supposed to be displacement over time. So the displacement have to care about direction. So therefore, the 11 meters should be positive, and the 25 meters that I'm adding is a negative 25 meters because it's going to the south. So therefore, it becomes 11 meters minus 25 meters, which is negative 14 meters. So that's your velocity then. If you have your velocity equation, which is displacement over time instead of distance over time, displacement over time. So therefore, it's negative 14 meters over the time of 12 seconds. Now, so the negative will actually survive. So 1.17 meter per second, negative 1.17 meter per second. So you can leave your answer like that because in this question, you're not breaking from normal. We are using north as positive, south as negative, which is the normal thing that people do. If you're doing the normal thing that people do, you can just leave your answer like that, and then people will say, okay, yeah. So if you're looking at this number, 11 meter is positive, then of course negative means you're going south. So you can leave your answer this way, or alternatively, you can also say 1.17 meter per second, and then just put the south as direction. And then don't put the negative, right? So that is also right. But don't put the negative in there though. Okay, so a few more examples. How long does it take a car traveling 45 km per hour to travel 100 meter? Now, first of all, you look at this unit and you go like, ew, that unit doesn't work with any of the equations, right? You cannot have km per hour. So remember that. So therefore, the step one is actually getting rid of that km per hour business and change it to meter per second. Now, hopefully you remember the shortcut. Km per hour to meter per second is dividing by 3.6. So use the calculator, divide that by 3.6, you get 12.5 meter per second. And now this number we can actually use. This is our speed or velocity, right? If there's a direction, it's a velocity. If there's no direction, it's a speed. Okay, so what is that 100 meter? Look at the unit tells you that really distance. So therefore, you have your distance, velocity, and the question is asking for how long is in a time. So you're looking for time. So the equation originally is velocity equal to distance over time. You're looking for time. So you can solve the equation for time first, or you can plug the numbers in if you're very comfortable with yourself. So you say 12.5 is equal to, where's my displacement? 100. So 100. And then where's my time? So I'm looking for time. Okay. So you have that in here. Now, solving for time. Okay, so I'm not going to, again, right? So I think I said it yesterday. We're only going to do algebra for one day. So I'm not going to explain where this comes from. Okay, you should know. And 8 seconds is the final result. 8 seconds. Okay, moving on. Lex. You can always pause the video and rewind if I'm going a little bit too fast. How far does a skateboarder travel in 22 seconds if its average velocity is 12 meters per second? Okay, same idea. 22 seconds is a time. This 12 meters per second is a velocity, or they didn't really give us direction, so technically it's a speed. But that's okay, that's okay. Now what you're looking for is displacement. So velocity equal to distance over time. Distance is velocity times time if you rearrange numbers a little bit. So therefore, velocity times time, 12 times 22. That's it, right? 12 meters per second times 22 seconds. And that's 264 meters. That's your displacement or distance travel. Because I don't really know the direction, so I guess it's only like a distance travel. Number 3, a shopping cart moves from a 0.3 meter west of a flat pole to a 0.80 meter east of the flat pole in 2.5 seconds. Find the average velocity. Okay, so this, it's better that we draw a picture. This is a flat pole right here, and so that's the ground. Now, you are actually moving from this location, which is 3 meter west from the pole itself, to a location 18 meters. So you're ending up here. Now, so this is 3 meters from the west, and you ended up moving to a location that is 18 meters east of the flat pole at the end. Okay. All right. So average velocity. So velocity. So we need displacement. So that means I actually care about direction. Okay. So if you care about the direction, well, how far did you actually travel? So you go from this location to this location. So how far do you actually move? You move a total of 21 meters. Like this is your change in position, right? It's 21 meters. It's 3 meters plus that 18 meters. So your change in location. So that means the first time I look at you, you were over here. And the second time I look at you, you are over here. So therefore, in my conclusion, that you have moved 21 meters, but Which way? Well, because you're on the west first and then you go to the east, you move 21 meters to the east. So from your current location, you move 21 meters to the east. Okay? So therefore, that's my conclusion. This is your total displacement. You walk 21 meters to the east. Okay? Now, if you want to, like, if you remember, like we said, displacement can also be obtained by using the change in your position, right? So that means your final position minus your initial position. So F stands for final, the subscript initial, I is initial, F is final. So think about it, it also worked this way. Now at the end, where are you? At the end, you are 18 meter east, right? That's your location. You're 18 meter east. Okay, so 18 meters and minus initial. Initially, where are you? You're 3 meters west, but remember, west is negative. So therefore, it becomes 18 minus negative 3, which gives you 21, right? 18 minus negative 3, so that double negative actually works out. So you can think of it in two different ways. If you can do that picture in your head, you know that it walks 21 meters. Otherwise, use the equation. Displacement is final location minus initial location. Just remember, your location can be positive or negative depending on if you are south or west, or south or north from the origin. The origin is where 0 is. So velocity, displacement over time. So 21 meters over time, 2.5 seconds according to the question. So in your calculator, that's 8.4 meters per second. Now, because you're walking toward the east, so that means your movement is toward the east too. So 8.4 meters per second east. All right, so that's it for the first section. So I will assign a few questions for you to do. It will be on the course webpage, of course, along with this video link with the post. I will actually do a couple of these worksheet questions in class when we meet again on Wednesday. I would like to explain a bit more, especially question 9 and 10. So you won't be doing question 9 and 10. I'll tell you which question to do, but it's definitely not 9 and 10. All right, so take a break right now, I guess. Start working on some of these questions and take a short break and then come back and watch the second video. Thank you. Bye.